floor is yours.
Okay, thank you. My name is Fred Busing. This is Kees Post, and we will alternate. So it's not me before the break, me after. So it will alternate depending on the program. So where we are, I'm more into this simple stuff, wires, pieces, metal, and he's more in the real applications. And I say, okay, let's use the same things in the complexity. But we can alternate so that I explain a piece, then he does some of his stuff, and so on. So that's the idea. So we give it this. This has a little music with it, I think, the movie, but maybe it's just the speakers here, so but we don't need really a lot of noise. No. Okay. Airplane. Could be a car, eh? Okay. It happens to cars also. You can question what do you want? What do you want the systems to do? Stop? Or go into 50 minutes break and then recover? Well, that's an interesting question. If you do a system, if you build a system, what do you expect of it? It has to work continuously, you have to do something. This is the other edge of the spectrum, radio interference. That's really very tiny signals, noise, but that's what they call emission. Emission is the noise that other people have problems with on the radio. And this end with the plane was a susceptibility or immunity problem. The civil standards talk about immunity, the mill standards are about susceptibility. It's the same thing seen from the different sides. So both aspects are there in EMC, so that's a good addition. The ability of the system to operate according to specification in the intended electromagnetic environment. And that means if you have something for the home, it has to be able to work there. Usually the fields are a little less. And if it has a car, it has to work in the environment where the car is supposed to be, so on the street, everywhere, so like the plane out in the open. And then there's the industrial environment, which is somewhere in between. It's a little less than everything in the outside world, but a little more than in the home. So that's different levels. And then here, without generating unacceptable electromagnetic emissions into the environment. So these two aspects are the essential requirements of EMC. And that's what's written in the EMC directive. There's 3 criteria. No emissions, that's as old as the radio. As soon as the radio was invented, you get interference. Then operates satisfactorily, which is more or less introduced when the EMC directive was introduced in 1996. So it has to work, and that's some sort of customer protection. If you buy something, it doesn't work due to EMC, you can bring it back and you get your guarantee. In America, they just do the top, and they say, okay, the bottom part, the market will filter out. You won't buy these things anymore, and will stop by itself. Okay, that's a different philosophy, but okay. And then the third thing, which is very important, it has to work. You see, this is a metaphor for a system which has a problem with itself. Actually, it's playing, of course. Okay, but it's very important that the system has to work. And you find that in some standards, other standards don't mention it, but usually if you go to a lab for measurements, first you work on the system until it works, and then you bring it to the lab and try. But the working is important. And in the mill standard, it's explicitly stated that you have to be compatible with yourself before you go see what others do. Okay, so these 3 things are important. And well, I talked about this plane. Performance criteria were also important. What do you expect? A would be system continues to work according to specification, no degradation. That's the plane with the lightning. You don't want to see anything. So it just has to go on for safety. B would be a little less. They say, okay, temporary degradation is okay, should recover by itself. So you see a flash in the TV screen or no, something goes wrong, but it comes back and everything is okay. That's B, and then C would be you have to kick it. Like your PC, if your power goes out, the desktop PC, power goes out, it stops, and you have to do something to get it back running. That would be C. And then D would be it breaks, but well, that's not a criterion, of course. But unsafe situation is never acceptable for the directive. So if it becomes unsafe, like the commercial of the Picasso car, where these robots, these painting robots start to do wild things by themselves, that's not acceptable. Okay, then we have the elements for an interference situation. You need a source to have a problem, you need a victim, you need a coupling path. And usually the source you cannot work on because it's there, like a radio transmitter. Is this better or less? It's working, okay. Radio transmitter, the victim could be a wheelchair, electric wheelchair, and they have to work together. The field you cannot remove, the wheelchair has to be in that area, so if they should be compatible, both have to work. If there's a problem, it's usually the coupling path. The coupling path you can work on, you can make it better, you can shield your cables, that kind of things. EMCs, for me, I think it's simple because it's always wire. Cables, wire. The rest is side thing. You can see that here. Yeah. This is a radio. This is my generator. It's on. No problem. And put this cable on. You have interference. So this cable is not suitable for what comes out of this box. But the box itself, it's okay. This is a different cable, a coax cable. No problem. This is two wires for the mechanical guys on the room. Two wires, internal wire and a shield. Okay, the coax cable. There's also two wires, a white and a black one. This is the same coax cable. This is not mine. Made a very minor change in this cable. I removed 3 millimeters of shielding and put a little wire around. And now it's almost as bad as this one. So yeah, it's always wires or interconnections that do it, from very small to very big. The bonding wires on the chip is also, and even the traces on the chip is an interconnection. So you can have EMC on that level. Usually the frequencies are a little higher. But okay, that's cabling. Wires are the antennas and receivers of electromagnetic noise. And sometimes the cable is transport medium by itself, and you have conducted interference. Okay, well, these effects appear at any scale. It has to do with the wavelength. Very big scale, let's say 150 meters, 200 meters, ship. And say, okay, a wavelength, 150 meters would be 2 megahertz wavelength. And then about 1/10 of the wavelength, you already see effects that we will see in the demonstrations. So for a ship, that could be a low frequency, or more medium wave. For a tiny printed circuit board, the interactions are much smaller, centimeters, millimeters maybe. And there you get effects in the megahertz, hundreds of megahertz, gigahertz range. But the effects are similar, comparable, but the frequency at which it happens depends on the size of your system. Example. Wheelchair.
Al zeker 4 keer schildert maar weinig of ooit thuis uit Lezing met haar scootmobiel een ongeluk veroorzaakt. Niet omdat ze niet kan rijden, maar omdat haar voertuig door een technische fout zomaar op hol kan slaan. Nu wil ze andere bezitters van hetzelfde type scootmobiel waarschuwen. Want volgens haar is het een kwestie van tijd voordat het een keertje echt